All right, so today we are starting on the pink Explore Polynomials Pear Deck intro. I decided instead of doing Pear Deck, we were going to do it on paper. So this is our first introduction to polynomials. I'd also like you to take out those new Unit 3 notes from yesterday that look like this, because we'll start referring to things on here as we start working through the pink sheet. So I just used a new word that you probably haven't heard before, and that word is polynomial. That prefix poly means many, and nomial means terms. So a polynomial has many terms joined by addition and subtraction. So we're going to go ahead and take a look at all of these different polynomials and see how their graphs are different on the calculator. So we've never used our calculator for graphing before, so I'm going to just kind of give you a rundown of the basics and how to find certain tools for your graph. Mainly for graphing, you're going to rely on the top row of buttons on your calculator. I've already got some stuff in there. Let's clear that out. So the top row of buttons are the ones that we use for graphing. We've got a y equals button. That's where we're going to be typing in equations. The window button you guys won't really have to do much with. The zoom button we might have to do some things with today, just in case anybody else has been using your calculator or if you're coming from taking a stats class. Trace we can use to trace along the shape of the graph. And then the graph button makes our graph. So these are primarily the buttons that we are going to be using. So step one is we are going to look at our equation, y equals x squared, and we are going to hit the y equals button on our calculator. So go ahead and hit y equals. And we see that we have a lot of different y equals options. This is because on your graph you can type in a lot of different equations at the same time. So for this one, we want to type in x squared. Now, from using the TI-30s, you may be tempted to use this x squared button, but that just puts that little exponent of 2 there, and I actually kind of want to get us out of the habit of using that button if you are familiar with it, just because in this chapter we're going to be dealing with lots of different exponents, not just squareds, but powers of 4 as well. So clear out any stuff that's in there. If anybody's been using your calculator ahead of time, clear out any equations in there using the clear button. And to type in x squared, what we use for the variable x is not this letter feature using the alpha key, but this variable button that has x, t, theta, and n on it. If you push that button, it automatically gives you x. Those other forms are different modes you can be in on your calculator. So x, t, theta, n button. Is how you get x. Now, to do an exponent with x, we, instead of using that squared button, because we're not always going to want a power of 2, we're going to use this little mountain button above the division symbol. This is called the caret key, and when you click that, on the older calculators, it might show as this with a parenthesis, but newer calculators should actually superscript you up to the exponent itself. So mountain button for exponents. And that is right above the division sign. So what power or exponent are we going to type in? 2. So there's our x squared.
We'll just hit the x squared button for 2 too.
We want to get out of that habit though if you are used to using that, because we're going to have to do lots of different powers, and there's a couple of finicky things that come up with the exponent itself. So if it is a quadratic, if you like doing that better, I guess you can. Just beware, because sometimes students will use that everywhere instead of typing in those different exponents as well. So once we have our equation typed in, step number 2 is going to be hitting our graph button. So go ahead and hit the graph button, which is on the opposite side as the y equals. So y equals to type in the equation and then the graph button. So go ahead and hit graph. And your graph should look like a U. If it does not look like U, flag me down and we're gonna come and see if there's any issues. Okay, issue number 1. We're gonna troubleshoot everything. If you got something like this that says error invalid dimension, if I go back to my y equals, there's nothing wrong with that equation. If we scroll down, there's nothing hiding in those other y equals. But you'll notice up above, we have a plot that is on. So check your y equals and see if your plot is on. Typically we use plots for stats. How you turn a plot off is second y equals, so second y equals to go to stat plot. Select option 4, which is plots off. Press enter, and it should say done. And now when we hit the graph button, there's Liam's quadratic.
Mine says error window range.
All right, let's take a look at yours. And this is good, folks, because if you are like me and you throw your calculator in your backpack without the cover on, sometimes random buttons get pressed, so it's nice to be able to troubleshoot different errors. So let's see what's going on with the Lathans. So here's what's interesting. No plots on for Lathans. The equation looks good. I'm scrolling down, and I'm not seeing anything mysterious hanging out in the y equals areas. So when I hit graph, we see that there is a window range error. Folks, if you are getting the same error message, or if you look like you have a zoomed in or a zoomed out version of that U based on what I was showing here. So if yours looks like a weird U, a lot of times the problem is your zoom. So hit your zoom button, which is right in the middle. And option 6 is zoom standard. Now, I care about this one enough that we're actually going to write this down on our paper. So zoom button, and then option 6 is zoom standard. And what this does is it reorients your window to a 10 by 10 coordinate plane. So it just centers it around 0, 0 and makes it look normal 10 by 10 graph. So I'm going to hit enter on that option number 6. And then it shows up. So zoom standard is a really good one that can reorient your graph because it could be looking at a plot that is now off. Is anyone else having any error messages? Yes. All right, so this is a great example. So look at Ava's graph here. It's like, whoa, that's the y-axis, and we're not even seeing tick marks. That's the x-axis way up there. We're going to do zoom standard to fix this problem too. Zoom standard. And my line is dotted. I'm not really sure why that is happening. So here is another thing we are going to write down. I don't want you to do this, but if you're at home and you're like, this stinking calculator won't work, I can't figure out what's going on, doing a hard reset is sometimes the best and easiest thing to do. So we're going to write reset. So to reset. I don't want you to do this right now, though, because that'll clear out the equation that you already have in there. And we're going to see if we can fix Ava's dashed quadratic problem. So the key sequence that you will do is second plus sign. And what you'll see above the plus sign on your calculator is it says MEM for memory. So second plus sign, write mem by it. And you will select option 7, which says reset. Press enter on it, obviously. Or I guess you can just hit the number 7. That's good too. We want to select all RAM. So 1, all RAM. Enter all RAM. And then you have to arrow down and select option 2, which is reset. And you should get a RAM cleared to show that it's done. But don't do this on your calculators right now unless you are also having a problem that we haven't troubleshooted yet. And folks, this will be posted on Canvas. So again, if ever you're angry and having problems with your calculator, I will post this somewhere that says calculator troubleshooting so you can fix most of these problems. So if we go back to the y equals and type in x squared, so x caret button 2, and hit graph, there it is, and it is no longer a dashed or dotted quadratic. Is anybody else still not seeing this U? Does anybody else need a calculator still? One thing with doing a reset, especially on the newer calculators, is it does affect the brightness. So I'll just show you what that does on mine. So second, memory, reset, all RAM, reset. See how my screen just got darker? To adjust the brightness on your calculator, this can be helpful if you're doing math in a darkened room like this. Or on the older calculators, it actually kind of affects the boldness of the text. You can hit second up to turn up the brightness, or second down to turn down the brightness. So second up, second down. And on the older calculators, again, it kind of affects the boldness of the text, so it can make it a little bit easier to read, either up or down with that. So folks, those are some basic ins and outs of your calculator, some troubleshooting things. These calculators are awesome, but when you're first getting used to them, there are a lot of annoying little things that can happen. Again, if you run into a problem at home, you're like, I can't figure it out, the reset option is great. Or take a picture of the error message your calculator is showing. Take a picture of your input area, like the equation that you're trying to type in. You can just airdrop those to me in an email, and I can help you troubleshoot from there. But don't worry, chances are you haven't broken your calculator. Sometimes just random buttons get pressed, like if I put a plus sign here, just a plus sign. Can I graph a plus sign? Is that an equation? Nope. And when I hit graph, it does the first one okay, and then it's like, no, syntax error. Syntax error usually means something like you typed in something that doesn't make sense. It's kind of like if an English teacher flags you with a red circle, like, hey, what's this punctuation mark? This shouldn't be here. So syntax error is kind of like a math punctuation error. So I'm going to get rid of that plus sign. And now it's all good. And what do we know about this equation? It's a quadratic. And specifically, this is the parent function. So where's the vertex? Where's the starting point? At 0, 0. And we're going to go ahead and just put in those other points that we know at negative 1, 1, and 1, 1. And swooshing through those. And we are going to put arrows on the end. If you're like, well, my calculator doesn't put arrows on its screen. That's because on your calculator, you can actually keep going up and up and up. If you zoom or if we trace. And it keeps going up and up. So my calculator knows that it goes infinitely up, but we need to always show on paper that it goes infinitely up. So I would just make a note. It says arrows. I wasn't as picky about arrows in the last unit, but this one, we start hitting it hard with some of the more fussy details with graphing because our calculator is going to be doing some of the heavy lifting for us. So, awesome. We have now graphed that first equation using our calculator, and we were able to pull out some exact points because that was the parent function. Now, in the instructions, it says, sketch the graphs and make observations about the exponents. So my highest exponent here is 2. We're going to see what this means for some of these other equations that have a power of 2, which is the next 3. In all 3 of these, the highest power in the equation is 2. Going back to the notes for a moment, we call that little exponent the degree of the polynomial. The degree is the highest exponent. So that parent quadratic would have a degree of 2. So degree of a polynomial is the highest exponent. So let's just say that this is degree 2. Actually, maybe we should write out degree, or DEG, so it doesn't look like domain. Our degree is 2. This one's degree is 2. This has a degree of 2. And if you're looking at this one going, what about that x? Folks, what is the current exponent of that x? 1. So just like plain old x has an implied coefficient of 1, it also has an implied exponent of 1. Now, even though this does have an implied power of 1 here, the highest power in the expression is 2. So this one also is degree 2. This one also is degree 2. What about this one? What's its degree? 4. So degree 4. What about number 6? Degree is 4 as well. Looking at number 7, what's the highest power in this equation? 4 again. So degree is 4. Ooh, look at number 8. What a nasty little equation. This also has a degree 4. And it's on number 9 that we encounter something different. This has a degree of 3. So we had 2s and 4s, which are even numbers, and then we have 3, which is an odd number. And we're going to see if that has any effect on these graphs. Let's go ahead and turn to the back page. See if you can state the degree for the next 3. Three, 5. So notice that in all of these equations that we looked at, the highest power was always in the first term. We call this kind of layout or format standard form. So polynomial standard form. The powers are in descending order. So standard form, the powers are in descending order. So if I had 2x minus 7 plus x cubed, y equals, is that polynomial in standard form? No. So we can switch the order of these terms because they're all joined by addition and subtraction. But we do need to make sure that we are locking in the sign with each of the terms it is associated with. We did this way back in Unit 1 a couple of times. Sign goes with the number behind it. And I like drawing those little boxes because this kind of shows the structure of the polynomial, that it is made up of individual monomial or single term parts added or subtracted together. So if I want to write this in standard form, who's got the highest power? X cubed. So x cubed, which is positive, will go first. Who comes next? 2x. And then the minus 7. So this is now in standard form, which I like to abbreviate SF. And it's nice to have the equations in standard form first because then I can identify the degree. Now, right now, the degree is just going to be something that we identify. It's like, all right, it's the highest power. That's really cool, I guess. What the degree is eventually going to tell us is how many roots or solutions the function has and how it will look. So it tells us a bit about the shape of the graph and how many roots or solutions it has. So mainly today we're just kind of going to be identifying the degree, saying, yup, it's the highest power, but it's eventually going to tell us quite a bit about the polynomial. So folks, let's go ahead and go back to our pink sheet and flip to the front side. So we have identified the degree. So observations about the exponents. Next it says positive a value versus negative a value. So the a value, actually let's change that. I want you to put positive LC and negative LC. Positive LC and negative LC. And what LC stands for is the leading coefficient. Your leading coefficient is the coefficient of the term with the highest exponent. So the term that gives you your degree also gives you the leading coefficient. And we're going to see if that tells us anything about the shape or structure of the graph. So folks, looking at this first one again, what would you say is the leading coefficient of this? What's the coefficient of x squared? It's 1. It's got an implied coefficient of 1, and 1 would be positive. So positive leading coefficient. What about our next one? What's the coefficient of negative x squared? Negative 1. So this has a negative leading coefficient. So our degree term is 2x squared. What's the coefficient of the term that gives us the degree? 2. So that also has a positive leading coefficient. Number 4 has a negative leading coefficient, negative LC. Ew, number 5 has a fraction as a coefficient, but it is still positive. Positive leading coefficient. Number 6 is negative LC. Try those 3 down at the bottom, indicating positive or negative leading coefficient. And remember, since all of these equations are in standard form, the leading coefficient is going to be your first number because that's the term that gives us the degree. So positive, positive, positive. On the back, negative leading coefficient, positive leading coefficient, negative leading coefficient. So here we have kind of outlined some of the main key features of polynomial graphs. They have an exponent term that is the highest, and they have a leading coefficient that can be positive or negative. So now we're going to go back and start typing these into our calculator and see if we can notice any patterns with what the graphs look like. Now, actually, without using our calculator, not forgetting what we just tested on yesterday, what's that negative out in front of that quadratic doing? That's a vertical reflection. So we know that this parent function pivots on the x-axis and looks like this. And we're just doing rough sketches, but the vertex still would be at 0, 0. Now on the next one, if you're looking at that going, ooh, is that +1 moving me up 1? And if it is that 3 stretching and the 2 also stretching? Folks, we have a problem here because transformation rules only work when our equations are in vertex form or transform form. It's fine on these ones where I only have one term, but over here where I have multiple terms, where there's no inside parentheses with x and I have this extra x term, I don't get to use transformations anymore. So what do we know about this graph? Well, not a whole lot. So this is one where we would want to use our calculator. So let's go ahead and go back to your y equals. You can use the delete key, but the clear button is actually faster. Clear just wipes out everything that you have on that line. And we're going to type in this equation. 2, the xt theta n button, caret button 2. Before you go any further, on the newer calculators where it automatically sends you up to the superscript, if I start trying to type that plus 3x, do I want that plus 3x up in the exponent? No, that's a problem. So after you do the power of 2 eyeballs, let me say everybody's eyeballs, something that I'm only going to say once. I'll probably say it a few times. To escape the exponent, see how I have that little flashy arrow up on top with the 2? You do exactly what that flashing thing tells you to do. You use the right arrow, so arrow over to the right, and that takes you back to ground level. So you say, I'm done doing exponent stuff, go further to the left, and it takes you down to ground level. Sorry, further to the right, and it takes you to ground level. So now we can do our plus 3x, and then plus 1. So we can write that down, that for this part, you arrow right to escape the exponent. Let's go ahead and hit graph. What do you think this is going to look like? Any predictions? It does look like it's another quadratic. So one of the other things it told us that we can consider as we are drawing these is the y-intercept, or where the graph touches the y-axis. So where does it look like my y-intercept is on this graph? It looks like it's at 1. And if I hit my trace button, go ahead and hit trace. It's like it heard me talking about it. So we can arrow over, and we can see that 0, 1 is an exact point. So hitting your trace button allows you to move along your graph and find points that are on that quadratic. So we're going to go ahead and draw in that y-intercept at 0, 1. That's going to be our exact point. So curving up, and then it sort of curves down there. And that was not a great quadratic. Let's try to make that a little bit better. Making it worse. So it is another quadratic, and it has a y-intercept of 0, 1. Going back to these graphs, what was our y-intercept for these two? Where is it hitting the y-axis and also the x-axis? 0, 0. So here, my y-intercept is 0, 0. And here, my y-intercept is 0, 0. Interesting. So these two simpler equations, y-intercept of 0, 0, this more complicated one had a y-intercept of 0, 1. What else is similar or different about these graphs? They're all quadratic, so that they have in common, and that has to do with that quadratic identifier, or that power of 2. So if that's the case, what should number 4 also be? It should be a quadratic as well. So let's put a note by these ones that says all quadratics. Number 1, number 2, number 3, and hopefully number 4, and we'll see about number 5. Other differences. 2 of those graphs are going up on both sides, and then this graph is going down on both sides. So that was one of the other things it told us to look at is the end behavior. What are the ends of my graph doing? These are going up. These are going up. And these are going down. So let's see what happens with this next one. Now, before we type it in on our calculator, make a prediction. Where do you think the y-intercept will be? It's got to be 0 something. And which way do you think the arrows are they going to go? Are they going to go up or are they going to go down? Up or down. So just make a prediction. And now let's test that theory. Let's go ahead and type this equation in on our calculator. Negative 2x squared plus 3x minus 2. Don't forget, when you do the caret button 2, arrow to the right to escape your exponent to bring it down to ground level. Is anybody not seeing that graph? Is anybody not seeing that graph? I'm here to help troubleshoot all calculator problems. So, where is our y-intercept? I hit my trace button. It's at 0, negative 2, and I can tell it's at tick mark negative 2 on my graph. So 0, negative 2. Is anybody correct with their prediction? If this one has a y-intercept of negative 2, and this one has a y-intercept of 1, what if I told you to find the y-intercept without using your calculator to graph? How did we find the y-intercept when we were doing standard form? So if I had like 2x plus 3y equals 6, and I asked you to find the y-intercept, which is 0 and a number, what we would do is plug in 0 for x, which obliterates that term, and then solve for y by dividing both sides by 3. And y is equal to 2. But ultimately, if I want to find the y-intercept, we plug in 0 for x. Folks, if I plug in 0 for x, 0 squared is 0, 2 times 0 is 0, 3 times 0 is 0, and y equals 1. Ding, ding, ding. Our y-intercept is 1. So if I wanted to find this y-intercept, which is always 0 and a number, I plug in 0. 0 squared is 0 times negative 2 is 0. 3 times 0 is 0. So it's kind of like I get to cover up both of those x terms. And we are left with the constant negative 2. So we're using our calculator to explore, and we're kind of starting to see how the equations for these can tell us some stuff about the graph. Now, let's go ahead and draw the rest of this quadratic using that y-intercept as an exact point at -2. So we're going to curve up, and we don't quite hit the x-axis, and then we come back down. And this graph was going down in both directions. So, is number 4 quadratic? Yep, sure looks that way. So, let's see what happens with number 5. Go ahead and go to your y equals and clear out any stuff that's in there. Now, I know many of you are looking at that fraction going, I don't see that friendly little ABC button or mixed number button like we had on the old TI 30s. To enter a fraction in on your calculator, this is going to be a very short process. If I want 1/2, I type it in as a tiny division problems. What is 1/2 if we're talking dividing? 1 divided by 2. And on your calculator, that will look like 1/2. Some students like to trap that in parentheses, which I sometimes do when we start typing in more complicated equations just to keep track of it. But you don't have to have parentheses on the problems we are doing right now. So let's practice that. Here's 1/2, so I'm going to hit the 1 button, the division button, boop, and then 2. And that gives 1/2, or 1 divided by 2. Then hit your xt theta n button for x. Now when we use the caret button, we're going to type in 4. What do you think it's going to look like? Does it quite look like a quadratic? It's kind of like wider on the bottom. It's a little bit different, so I'm going to try to do my best here. Also take note, what was the y-intercept on this one? 0, 0. If I plug in 0 for x, 0 to the 4th is 0 times 1/2, it's 0. So 0, 0 is my y-intercept. And then I kind of get this kind of wide U. With arrows going up. So it kind of looks quadratic-ish, but by definition, this is not a quadratic. If you're like, why, Mrs. Cairo? Because it doesn't have a power of 2. Quadratics are only degree 2 polynomials. This is a quartic or just another polynomial.
So what is it?
You can just say it's a polynomial. Yep, so quadratics we have kind of special name for. It's kind of like cubics, but kind of anything higher than 3. We're just like polynomial. Okay? So let's go ahead and take a look at number 6. What do you think the y-intercept is going to be for this one? If my y-intercept is always 0 and a number, if we plug in 0 for x, 0 to the 4th, 0 times 0 times 0 times 0 is 0, times -2, it's 0, and then I add 3, and I get 3. So with that, using my calculator, I know that the y-intercept is at 3. What else do we know? We know that maybe it's going to look like this stranger looking U graph or this sort of flatter quadratic. And then we've got that -2 in front of it. Make a prediction about what direction you think the arrows are going to be going in. Go back to y equals. Use your clear button. Hey, real quick. if I type in -2, am I going to use the minus sign or the little negative? The little negative. And if you're like, what little negative, Mrs. Cairo? So to the right, these are your operations buttons, like minus, so like 2 minus 3. But if I need to make a number negative, we use this negative down by the decimal point. So you'll know when to use the negative, because if you like read the equation in your brain, you wouldn't say minus 2x to the fourth. You'd say that's negative 2x to the fourth. So use the little negative, 2x, caret button 4, arrow over to escape the exponent, because we don't want that plus 3 up in the exponent. We want it at ground level. Hit graph. Interesting. So we've got kind of that flatter topped quadratic, and it's going down. So going up and then coming down. So this one is going down on both sides. Now, our next one, what do you think this one's y-intercept is going to be? Anybody? 2. So if I plug in 0, it's kind of like we're using the cover-up method on both those x terms. 0 to the 4th times 2 is 0. 0 cubed times 2 is 0. So what we're left with is 2. So the y-intercept is 0, 2. So, woohoo! We have an exact point. And if you're like, why don't we just plug in some other exact points? 0 is pretty easy to plug in. Do you want to cube 2? Or sorry, take 2 to the 4th power, multiply it by 2, and then take 2 times 2 to the 3rd plus 2 by hand? Not really. So the y-intercept is a fairly easy exact point, but doing an input-output table for this, or even a parent table, would be pretty messy. So let's go ahead and see what happens when we type this one in. Y equals, clear out the stuff that's in there. Ooh, and actually, folks, I want to show you what happens if I use the big minus sign for that last one. So if I use the big minus sign there, calculator goes, you have a punctuation error and you can't use that big minus sign there because it has to be something minus something. If it's just a negative number, we have to use the little negative sign. So again, that's another type of error message that you can see on your calculator. So let's type in this one. 2x to the 4th plus 2x cubed plus 2. Ooh, does it look like an exact U anymore? There's something weird happening in there. Now, if you want, we can get a closer look at that weird little part by hitting zoom and selecting zoom in. And if I arrow up to that area I want to zoom in on and press enter, yeah, that doesn't look like a U anymore. It's got this funny little regroup, just a little bump in it. Now, folks, if you did try zooming in, I still recommend that you always reorient your graph to a 10 by 10 by hitting zoom standard. So zoom button, and then option 6, which is zoom standard. Another helpful thing, you guys are all probably Chrome browser users for the most part, maybe Firefox, hopefully not Safari or Internet Explorer, but these buttons up at the top, they're kind of like tabs where they take you to different parts of your calculator, particularly for the y equals the window and the zoom. So this takes me to the zoom tab, this takes me to the window tab, this takes me to the equation tab, that takes me to the graph tab. They're all kind of interacting with each other, but if you want to think of those as kind of different tabs, that's how your calculator is working. So let's try to graph this weird little thing that we got here. So it looks like it kind of curves up a little bit around the y-intercept, so I'm going to go like this and just do a little bloop up. Kind of like that. It's just a sketch. It's not perfect, but these power of 4 graphs are no longer looking like quadratics. I added in that cube term, and it's starting to look a little funny. I want you to take a look at number 8. What's the y-intercept going to be for this one if we cover up all the x terms? 1. Y-intercept is 0, 1. So I'm going to plot that exact point there. I want you to predict if our arrows on the end are going to be going up or going down, and what the shape of this graph is going to look like. Now, I, for one, would be like, I don't know. After we got that weird little shape, no idea. So, folks, to save you a little time on this one, it has the same first 2 terms. So this would probably be a case where I would arrow over and just delete those last 2 terms. Now, for this one, am I going to use a little negative or a minus sign? How do we read this? 2x cubed minus 3x squared? I said minus, so we're going to use a big minus sign. So minus 3x squared plus 1. Oh, getting a little funkier here. Let's go ahead and try to sketch this graph. We are going up. We go down, and then we go up through that y-intercept, and then we bloop back up. Making sure you're drawing arrows on your graph. Now, I want to show you what happens if you didn't use the little or the big minus sign here. I didn't do attendance. Oh, hear the rain. I'm so sorry. We have everybody. Thank you. All right, folks. So when we tried to use a big minus sign up here, we got an error message. I want to show you what happens if we accidentally use a little negative here. And we're going to compare these 2 graphs. 2x to the 4th plus 2x cubed. Do you guys think it's going to make a difference or not? Let's see what happens. So the blue line is what we should have. The red line is with the little negative. We're getting the spinning wheel. That's how we know it's working. Uh-oh. It's still spinning. It's still thinking. Ooh, so did we get the same graph? We did not. So, folks, this is why I like to spend a lot of time on just how to make your calculator do what you want it to do. It's a very sophisticated little machine, but you've got to be smarter than it to know what you actually want it to do. So if you're wondering, why is it showing a completely different graph? I'm going to show you how your calculator would interpret this. So if I do 2x to the 4th plus 2x cubed, and then the little negative 3x squared plus 1, if this is little, your calculator's like, oh, you're not subtracting 3x squared. You're taking the opposite of 3, or that's negative 3x squared, so you must want to multiply those. That's what your calculator has done with this problem, is it is interpreting this as times a negative 3x squared instead of minus 3x squared. So the little negative means that is a negative number, and your calculator autofills the operation in as multiplication. So if you read it as minus, use the big minus sign. All right, folks, so at this point, all of the graphs that we have looked at, where's that? All of these graphs so far have been even degree. So in the margin here, let's write E, V, E, N, even degree. This marker is awful. Even degree. This has a degree of 4. It's an even number. This has a degree of 2. It's an even number. So what is the difference between an even degree graph and what we're going to see next as an odd degree graph? Can we still find the y-intercept in the same way? Well, what would our y-intercept be for this one? Negative 2, that constant term. If we plug in 0, we cover up that whole term. So y-intercept, 0, negative 2. So now, let's see what this graph looks like. How different will it be? What can we expect? Well, this one shouldn't be too mysterious because this actually is a manipulation of the cubic function. What's that minus 2 on the outside doing? Down 2. 4 getting multiplied out in front, vertical stretch. So we should know that this should look like a stretched version of the cubic function that has been moved down 2. Now remember, don't forget to arrow over to the right to escape your exponent to put that minus 2 at ground level. Does it look like a cubic function that has been moved down 2? You betcha. Not my best cubic. That's okay. So if you're like, well, I wasn't really expecting, I don't know what I was expecting for a change from even degree to odd degree. But here's where the change occurs. Instead of having both arrows going up or both arrows going down, our graph is now doing a little disco dance with one arrow going this way and one arrow going that way. So this one is going up and this one is going down. Folks, we're going to take a quick breather before we move on to